Okay, quick review. Okay, it's going to be important in this section. Hey, it's going to be important in this section that you make sure that your V's are either small or large, whether it's volume or velocity. Nothing? All right, don't forget pressure is mass, no, force over area. What the heck am I doing? Force over area. All right, and our units over here are kilogram per meter cubed, pascals, which is the same as a Newton per meter squared, and meters cubed. All right, make sure you got your units correct. All right, now this mysterious thing called pressure, which we've talked about already in gas laws. What the heck is pressure exactly? First of all, you need to understand that pressure is not, I repeat, not a force, okay? And technically, pressure doesn't really have direction either. Pressure is in all directions, okay? You don't get a, well, like for instance, come here, Rudy.
Because I asked the question, that's why.
All right, why you have your backpack on? You running to leave?
Because I don't take it off.
It's a safety blanket.
Is this Linus blanket? All right, look that way. All right, now there's air inside the room, right?
Yes.
Dude,
The air is made of molecules, right? Molecules are all bouncing around, right? So they're
No. Yeah, I refuse to believe that.
So they're all bouncing around, and nice hair.
What are they bouncing off
Envious
of?
of your hair. Wait.
Mr. Bruin, you can use that as a wig.
Ooh, I could.
What is that?
Turn to the side.
Yeah, that was the tail.
Is that real?
There we go.
Is it real?
Yeah.
Of course it's real. Can't you tell? Mine's softer.
Yeah, well, mine has more volume.
And it smells good.
All right.
I use that.
Hot.
It's not you having hair, oh no.
I am not. Okay, so gas molecules are coming in and bouncing off of Rudy's head, right?
Yeah, so you can hit the
And they're bouncing off shoulders, chest, nose, and all that. So here's the deal, though, is that which way is the pressure? Okay? Well, they're bouncing this way and bouncing off, right? And then some are bouncing this way and bouncing off, right?
Some straightforward.
Yeah, so what happens is the pressure is in all directions, pressure from all sides, but the force from the pressure is always,
In one direction.
and always in one direction. That direction is always perpendicular to the surface. Okay, so the pressure is like this direction, or this direction.
I'm getting beat up by air.
That's right, or, look at that nose. This direction. Okay, you can say that.
Yes. You can't say.
So yeah, so like, here, we'll make fun of myself then. So the pressure on my head in these directions, right? Always perpendicular to the surface, okay? Because the gas molecules are always bouncing off the surface. And what happens is that the forces, when it bounces off this way, it gives the surface an impulse to the right and down. But then there's other ones bouncing this way. They give an impulse to the left and down.
So the left and right cancel.
Yeah, the left and right always cancel out because we have random motion in the molecules, right? And so what we end up with is a net force always perpendicular to the surface.
So the net motion is not random.
The what?
The net motion isn't random.
Say that again?
Net motion is not random.
That, well, not when there's a surface there. That's correct.
Because nothing can come out of the surface.
We have two causes for pressure. I just showed you one. The first cause for pressure is because of the random motion of the molecules and their collisions, one by one, on a surface. Okay? So that causes a pressure, which is related to a force, and the force is always perpendicular. Okay, what happens to the pressure as the temperature increases?
It increases up.
Why?
More collisions.
Most collisions.
Yeah, because the molecules are now, on average, moving faster, and therefore more collisions with more kinetic energy in the collision, so therefore a larger pressure, and therefore more force from the pressure. Okay, that's called thermal pressure. Okay? As the temperature rises, there's more thermal energy, therefore more pressure. Okay, so pressure, number one, is caused by this thermal effect. Okay? All right, there's another reason why we have pressure. The other reason why we have pressure is because the fluid as a whole interacts. Okay? If we look at like a container full of a fluid, all right, and it's filled with fluid. Okay, this molecule right here has no overall net desire to transport anywhere, right?
Right.
If it's just a static fluid, it's just sitting there. Okay? Now, but wait,
There's one.
there's all of this column of fluid above it, right?
Exerting the force.
Yes.
And gravity pulls that fluid down, right? Right?
Yeah.
So that means that this spot in the fluid must support all of this fluid above it, right? So wait a minute, but what about this spot? It only has to support this much fluid.
And then one below that one has to support it. Plus
And the one, yeah, and so like what happens is that this point has to support all of this plus the difference in between, right? So what happens is where will the pressure be greater in the fluid?
Bottom.
At the bottom, because it has to support so much more weight of fluid above it. Does that make sense? So we get another reason for pressure. The second reason for pressure is because the fluid is connected, and the gravity on Earth pulls the fluid down. Now, if we were in space, in a zero-G environment, or in weightlessness,
there's no pressure.
there would be none of this gravitational pressure, because gravity wouldn't be pulling the fluid towards one direction. Does that make sense? So, on Earth we have gravitational pressure. Pressure because of gravity, the gravitational effect, and we have a thermal effect. Now, here's the deal, everybody. We have two types of fluids, remember? We have gases
And liquid.
and a liquid.
That's a nice element.
I know, it's kind of slanty.
Wow.
It was pretty.
You liked it?
Yeah, I wasn't being sarcastic either.
I like it.
He looks unhappy. All right, so we have gas and a liquid. All right, now, in gases don't have a lot of mass. So therefore, since they don't have a lot of mass,
They don't build up so much pressure.
yeah, they don't build up so much of this gravitational
So
effect,
we don't
right?
feel it so much.
Now, we do feel it.
Yeah.
In fact, here where we're at, we have what we call atmospheric pressure on us, right? And where we're at, 1 atm, because of all the air piled up on top of our head. Actually, even when you're inside of a building, okay? Even when I'm inside of a building, it's like, well, I only have this air from here to the ceiling, right? Well, but this building is not sealed, right? It's connected to the fluid outside because through doors, open doors, and leaks and all that stuff. Now, there are buildings that are sealed. Some of you walked into some of these buildings. Usually they'll have like a rotating door in the front, and when you walk through the door, sometimes you'll feel a change in pressure in the building. Or if you happen to use the handicap door and open up the door, you'll feel a breeze coming out of the building towards you. You ever been into one of those buildings where you open the door? Yeah. Like down here, like down on the last bottom floor, you'll feel a breeze sometimes. Especially when you open the door, like by the cafeteria, sometimes you'll feel a wind blowing out. Or if you're out by the dock, right? If you go out by the dock, the wind is always blowing out because there's a higher pressure inside the building than there is outside the building. All right? But this building is not totally sealed. All right? So we still have, in a sense, even though we're in the building, we still have all this air stacked up on top of us from the atmosphere. But here's the deal. Unless you have a tremendous height of air above you, the gravity effect is minimal in a gas. So we neglect the gravity effect in gas. Unless you're talking about like atmospheric pressure or you're traveling a really great distance. If you go from like the top of the Empire State Building to the bottom of the Empire State Building, your change in atmospheric pressure is less than 1%. I mean, it's really small. Okay? So we're going to neglect the gravitational effect in gases unless we travel a tremendous distance. All right? But in liquids, so in gases, the thermal effect reigns supreme. That's what gives us most of our pressure in a gas, the temperature of the gas. In a liquid, on the other hand, since the liquids have lots of mass, the gravitational effect has a bigger influence on pressure than the thermal effect. You can increase the temperature of a liquid, and the pressure will go up a little bit, but not very much compared to the overall pressure because it has so much pressure due to the mass of the liquid above it. Okay? So generally in gases, we talk thermal effect. Generally in liquids, it's mostly because of gravitational effect that we have pressure. Okay? All right. And a key thing to remember, that in a fluid that's static, in any fluid that's static, the pressure must increase as you get deeper into it, simply because you have more fluid stacked above it, right? Okay. General rule of thumb.
Wait, what was it again?
So in general, then, the deeper you go in a fluid, the higher the pressure is going to be. Now, in a gas, we'll tend to neglect
But
it.
you said that's in static, right?
And for a static fluid, that's correct. In fact, let's just work that quick. We can work it out and derive it real quick.
Let's say my pressure, 10,000 feet below. So, exactly. You just said that right. Huh?
All right, here we go. Let's look at this spot right here. A horizontal line drawn across. Actually, I supposedly have a three-dimensional drawing here, so this horizontal level right here. Okay? All right. If it's a static fluid, it's in equilibrium. Static meaning it's not moving, there's no net force on it, so therefore the acceleration is zero. That means at this line, the force is up and the force is down must be exactly the same. All right? So what forces are down on this level? Well, number one is
Gravity.
all of this weight. mg from the fluid above. Right? Okay? There's more than just that, though.
ATM, 1 ATM.
Yeah, we have the possibility, if it's open to the air, of having pressure from above, pressure from the air or just outside above. Okay? And that will also apply a force. But wait a minute. mg is a force, but this right here is a pressure. How do I convert this to a force?
Over area.
I multiply the pressure from the air above times the area. Very good. Pressure times area gives me a force down. So I have this force from the air pushing down, and I have the weight of the fluid above this spot pushing down. And for this to be in equilibrium, then the fluid itself must push up the force from the fluid. All right? So that means that the force from the force inside the fluid there must equal the mg of the fluid above plus the pressure of the air times the area. Okay? All right.
But that's the bottom fluid, right?
What's that?
The force of the bottom fluid.
This is the force that the bottom fluid must push up. That's correct. Or at that spot must have a force up. Okay, I'm going to divide all the sides by area. And when I do that, these areas go away and I get the pressure from the air above. And right here I get mass over area. What the heck's mass over area?
Pressure. Oh, force.
mass?
No, density. Oh wait, over area? No.
No.
Over volume?
It's close to,
Pressure.
it's close to density, right?
But not quite.
But not quite, okay? Because this is mass over volume. But I could turn this into volume, right?
Yes.
If I want to turn it into volume, what could I do? I mean, area times, this is the area, right?
Ton
That's the
height.
height.
Times the height, right? So if I multiply the bottom times height and the top times height, is that okay?
You get density times gravity.
So I would get, this is now volume, right? So mass over volume is equal to what?
Density.
Density. And then times G times H, right? And over here, what would this be then?
P.
Force over area.
That's just the pressure at that spot in the fluid, right?
Yes.
And this is the way you normally see this written. The pressure in the fluid equals P naught plus rho GH. Okay? Make sure you can designate the difference between your rhos and your G's and your P's, because they all kind of look the same. All right? So the pressure in the fluid equals P naught. Now P naught is any pressure that's on top. Okay? Now, in our case, in most cases, it's going to be the pressure from the air. All right? And then rho GH is the gravitational effect. That's the pressure due to gravity. All right? And that's our first equation. It's called the static pressure equation. And I would like for you to write next to it, it's the pressure due to
Gravity. Gravitational force.
gravity due to pressure due to gravity or pressure due to the gravitational effect. All right? Something like that. And that's where that comes from. So, here you go. Let's say that you're home and here's your lab for tonight. Go take a bath.
That's a
My bed's not that big.
Lay down in the bottom of the tub.
Yeah,
I can't lay
that's
down at the
too-
bottom of the tub, baby.
5 feet.
And then go to the Trinity River.
Oh, I would not want to go in there.
No.
My ears are
Unless I wanted to die.
And,
What
Do
is
you know how many carcinogens are in there?
okay, go to the Trinity River first.
Go lay down.
And then go take a bath. Do it in the proper order. Okay, so if you're in the Trinity River and you're at a height or you're at a depth of H below the water, then go home to your bathtub and do the same thing. In which case will you get more pressure?
Trinity. Well, if it's the same height.
At that, in that picture, they'd be.
Well,
Now, assuming Trinity water
it's fresh water.
has the same density as your bath water, which may be in doubt. Okay? May be in doubt.
Okay.
There may be heavy metals in it, so.
What about sharks?
Or sharks.
Or the direct fish from Simpsons?
Hey, now here's the deal. There's no difference in pressure, is there? It's weird. It seems like because you're in a larger body of water, it should make a difference, right? It turns out not to make any difference at all. Now there's, well here.
Nah, they had different sea life. Now, if you were deeper in depth.
But, yeah, so what if you're in your 15-story penthouse?
First of all, I am not church.
15-story.
You're in Rudy's house on the 15th floor of the state penitentiary. Oh, I'm sorry. Nothing. So you're so you're in your 15th floor penthouse and you're in your tub. Does your height above sea level make any difference?
No.
Yes.
Yes.
Well, slightly. Not much, though.
Does the density of the water change?
No.
Does gravity change? Well, not enough to measure. Does the height or depth that you're in the water change?
No.
No. Now, the only thing that might change would be the air pressure on top, but we're assuming the air pressure to be very little different, right? So it would be the same pressure. Okay, so y'all know what water towers look like, right? So water towers look like this. Some of the older ones will look like this.
I've been waiting, sir.
There'll be some great big ones out there. Some of them actually have extra legs on them, some of the really old ones. The newer ones generally look like this. Okay? All right, and they put water in these things. Okay, so I propose to build my water tower like this. There's my water tower. It's a straw.
Doesn't hold us.
Will my water tower produce the same pressure as these other water towers?
Yeah.
Absolutely. The exact same pressure. Why do I not get the contract to build water towers?
Because it's not very one
Yeah.
itty bitty one.
Because one person flushes their toilet and my water tower is empty, right? The reason why they have the big reservoir at top is simply because when people are flushing their toilets throughout the day, this drains out. And they want a big reservoir, because if you flush your toilet once, then this one's empty. And so now it changes the pressure, right?
Big toilet.
They don't just put it at the bottom.
Put what at the bottom?
The bigger barrel.
Okay. The reason why they don't put the big part at the bottom is because if you just put the big part at the bottom, and you'll see water tanks like this,
Height.
is the height difference.
Yeah.
Okay? Now, what they do in a area that's hilly,
It's the stuff.
they'll just put this
Massive.
On a hill.
on a hill. So here, there you go. There's your water tower on the top of the hill.
Why am I so thinking about it?
Why are you
Because
bathing
think-
in the water tower?
So the height of the background does make.
Wait, but it shouldn't even be called a water tower.
So wait, what's that?
Wait a minute. Now, why do they do this? Well, first of all, here's your house.
So you just
And if you connect a pipe to your house, then the only difference in height is this, right? So that's the pressure you get in your house. But if you connect it to this water tower, then you get all of this height. So you get much greater pressure, okay? If you live, listen, if you live up here,
Your pressure sucks.
yeah, and you turn and you have your tub here, and you open up the spigot to put water in there, spigot, that's an old-timey word.
I want
Then
the
what
water.
happens?
The water.
Yeah,
It's just like-
it'll drain out into the water tower. Yes.
Oh, because the water comes in and goes.
Because now you're the water tower in your house,
So
right?
basically, you can't get water from the down there.
Yeah, well you can, but not through gravity.
You have to.
You have to pump it up there.
Yeah.
So here's the deal. Water towers on our nice flat prairie land around here have to be stationed above the ground. If you're in a hilly area, they'll put the water tower on a hill,
On the highest
And you at the
hill?
bottom.
as high as they can get it.
What if
Okay.
there's a hill somewhere and it just grows and it gets higher? And then someone has their house.
A hill grows and gets higher. Have you been watering the hill? Taking care of it?
Of course. And the hill gets higher than the one that has the water on it. What happens?
Well,
You shouldn't put your house up there.
then, for instance, like people that live in the mountains, what they have to have is they have to have pumps in the water line to pump the water up. Like for instance, like in New York City, say, okay, or downtown Dallas, where they have really tall buildings. Okay, the water towers are not as tall as the buildings. So if you open up your water faucet, no water comes out, right? Because it wants to drain to the water tower, because it's lower. So how do they do that? What they do is they have pumping stations in the building that pump the water up to holding tanks. Okay? Now, you don't actually need a water tower to produce pressure in your house. You can just have a pump. The problem is that when everybody is awake at the same time, turning on the water faucet, getting a drink of water, flushing the toilet, taking a bath, all at the same time, the pumps can't keep up. So they either have two choices. Either build lots and lots and lots of pumps,
Which takes a lot of energy.
which takes a lot of energy and a lot of upkeep, or they have a few pumps that at night pump it up into the water tower. And then during the day, the water tower drains out. Does that make sense? It's because they have like 8-10 hours at night where people aren't using water very much and they pump all this water up to the top. Okay? Some of you might notice that depending on where you live, during the day your water pressure may not be as great as at night.
Because that's when it's fresh out of the top.
Yeah, because it's fresh out of the top and not so many people are using water, so the system is pressurized more.
And one more thing. So say since it has a small opening or drain, wouldn't that also increase pressure? Because it's all the water on top, so the small opening.
Actually, it turns out it doesn't matter. And that's a really good point, everybody. Look, this spot down here, actually what they do is they have a pipe that comes down. But if this pipe is skinny, or if like they fill the whole thing up with water, so water's all the way across, this pressure down here, it doesn't matter how narrow or wide that pipe is. All that matters is the height. Amazingly enough. Okay? So there's a story of, Holland, right? Holland in England. Most of that country, a lot of that country is very near or below sea level.
Holland?
Holland.
Do you say it's in England?
Did I say England?
Yes.
I'm sorry, in Europe.
It's
Sorry,
in
sorry.
Netherlands. It's
Yes.
part of Netherlands.
Yeah. Right. Netherlands,
Over there.
Holland.
Oh,
it's Europe.
Nobody wow, that was so
Right.
off.
Sorry, I said the wrong thing. So you got Denmark, you got Holland, you got
Oh, you know how to draw
France.
it. Oh my
Yeah.
goodness.
I'm gonna get my drawing
Portugal
mixed
and
up.
Spain. Off to the side.
Anyway, the little country next to Belgium, right?
It's the same country.
Okay, it's very low to sea level, and they had flooding problems, so they built these levees, okay, to keep the sea out during like high tide and low tide. And then they thought, hey, we can get more land. So what they did is their land was like really close to sea level. And so what they did is they built these things to keep the water out. And then they said, well, wait a minute. This ground goes out like this, and what we're going to do is we're going to build a new one right out here,
So it wants to leave.
and we will just pump the water out, and we're going to have new land. And so they've increased the size of their country by going out into the North Sea, building a big earth berm, and then pumping the water out. Yeah, so there's the problem. And so they live with having to keep these things sturdy, right? Because if these things break, well then they're going to lose a third of their country.
One of them knocks on it.
So, here's the story though. The story goes that,
You need to attack them.
the story is that one of these sprung a leak.
And some kid.
Yeah, and some kid, little kid sticks his finger in the hole and holds back the entire North Sea.
Wow.
Now, is that possible?
It's like a picture moment.
Is that true?
Yeah.
And the
Except
answer
through the
is
road.
absolutely
Yeah.
true.
It's
Oh,
through
absolutely
the road.
possible. I don't know if it's true.
I know.
Absolutely possible, because as long as the water's not like, 100 meters deep, as long as the water level is only, 10 meters deep or so, this pressure is the same. No matter how much water is back there, right? So you just stick your finger in there and wait for the troops to come and put a cork in it, right?
That's really cool. Like, it's
Just
like a little airport. Everyone goes there to it's
Yeah, you see a leak.
Yeah. Your turn.
And then like the little kid.
I have this.
I have no imagination.
I have this bendy straw. Here's my bendy straw, and I have water in it. Is it possible for the water to be static like that?
Yes.
If you change the pressure, like how do you
No,
think that
no,
one
no.
is?
It's open to the air here and open to the air here.
No.
No.
Okay, because here's the deal. Look. P naught, P naught,
No, no.
rho GH,
See, that's why I said it's open in the air.
rho GH.
Before.
Pressure here will be the addition of these two. Pressure here will be the addition of these two. Now look, that means pressure here is greater than here, so what's going to happen? It's going to go that way. Okay? You've all heard weather reports where they talk about, well, there's a high pressure system over here, and there's a low pressure system over here. That's what causes wind.
Yeah.
Blows from high to low.
Prove it wrong.
What will happen is that in a static fluid, the fluid will level out. Okay? That's why we have sea level. Sea level. Because the fluid all across the earth has leveled out.
Sea level is a lie.
So if I pee in
You lie.
I know it's hard.
You lie.
Get the pan marked out.
Whatever.
Sea level is a lie, mister, and you know it.
Now, what changes sea level too is the moon. The moon, because of the moon's gravity pulling on the earth, it pulls on the ocean, and the ocean will bulge out. And that's what causes the high and low tides.
So is that,
All right, what will happen is that
the United States?
Earth will bulge out.
And South America.
Actually, it'll bulge out on both sides
Maine is really big on your map.
Oh.
because of gravity.
What curve is that? That's the,
High tide curve.
Hyperbola, is that what you're saying?
That means in a static fluid, at any horizontal level in a fluid, it has to be the same pressure. Because otherwise it wouldn't be static, it would be dynamic, right? Okay. All right, real quickly, let's just do this quick. Let's say I have a tube. The tube looks like this. Looks like the big letter J.
It's a cane, it's upside down.
All right, let's say this is blood.
K, oh my god. Cane.
Blood in here.
Student's
Whose blood?
Your blood.
Somebody willingly or unwillingly?
Let's say the distance from here
Who said
to here is 2 meters. Let's say the distance from here to here is 1 meter. 1 meter. Okay. Let's say it's standard pressure,
Think about it, that's a lot.
standard temperature and pressure,
Depending on
STP.
how wide the tube is.
Okay. What's the pressure in the blood right there? Go. All right. A couple of things. First intelligent question. That's 1 ATM, but we need to know what that is. Okay, remember on average, it's 100,000 pascals. Now, hey, remember if you're doing electronic homework, you're supposed to use 101.325, right?
I used 100,000 the first time.
Yeah, and you got them all wrong, right? You worked them out right, but you were more than 1% off. Okay, so if you're working e-homework, you need to use 101.325. But on the AP test, 100,000 is fine. Okay? So that's 100,000. Any other intelligent questions?
What's the density, volume, and all that?
Density of blood is in your packet. What's the density of blood?
Are you serious? Is this going to be on the AP density of
test this
blood?
out.
1050.
1050.
Very good. It is 1050 kilogram per meter cubed. All right. Any other intelligent questions? Or you have enough information?
Bless you. Bless you,
I think that's all.
Hey, does it matter that it's over here?
No,
Where will the pressure be the same?
over there.
everywhere.
Over here? Over here?
The same height.
Oh, over here.
There.
Over here.
Yes.
That pressure is the same as that pressure because it's a static fluid, right?
Oh, wait, never mind.
Now can you do it? What will the pressure be here?
EO plus.
Pressure at that point will equal the pressure, whatever's on top, plus a rho GH, right?
Is it 9.81?
No.
No, it's 11029.
1.1 times 10 to the fifth Pascal.
There you go.
So it's like 101?
Yeah.
101.050, is that right?
101.
1-1.
It's
Oh, no, no, no.
10290.
029.
110290.
1-1.
Yeah.
11.
Oh, 29.
It's
101.
No, 110,000.
110,000?
Yeah.
1,000? Oh, you're right.
Yes, it is.
Yeah, it's
multiply by that
110,290. There we go.
There you go.
Is that right?
Yes.
That's right, because this is going to be
This
10,000.
at the bottom one.
Yeah. All right, we got it?
You didn't add it. Oh yeah, you did.
Yeah, add it to that. We okay?
Yeah.
All right. Hey, quick question. Where's your blood pressure greatest?
Right above.
Your feet.
In your top of your head.
Yeah.
Are you standing on your
At
head?
the bottom. My thighs.
Your feet will have the highest blood pressure.
Your
What if we lay down?
Ooh, what if you're laying down?
But it's not straight.
Then
Your stomach's
it's even.
high.
Yeah, well, that's not
you're
science.
posterior.
Well, unless you're dead, it's not straight.
Your heart's
Oh.
Nah, but your blood pressure, you're
You
correct.
also have valves.
You do have valves and all that, but listen, you have higher blood pressure down in your feet than you do in your head.
That's why if you
Just
ever
why-
hurt your leg, you're supposed to lift.
It's correct. So that, remember I always say if you have a part of you that's bleeding, what are you supposed to do? Apply pressure to try and close off the vein and elevate it to lower the pressure.
Really?
Yes.
Because there's no weight on it. As
Like if you cut your foot, you're supposed to bandage it and you're supposed to stick your foot up. Like lay down and stick your foot up. Because you have lower pressure. Because otherwise it's more likely to
And you're
bleed.
supposed to add ice to cool it down.
Hey, and if you don't believe that, then all I want you to do is to go home.
Break your
Cut
leg.
yourself.
No.
Get a sledgehammer. Break your leg.
Go home and sit in a chair upside down. You ever done that? Like on a
Feel
couch?
all the pressure on your head.
Yeah. Yeah, and like you put your feet over the back of the couch and then you stick your head down here. And then sit that way for about a minute. Or as long as you can stand it. Because pretty quickly you'll start to feel this throbbing.
Then why do you take purple?
What's that?
What's up?
Yeah, your face will turn
Because all the blood
brighter red and you'll have more pressure. And actually don't do it for real long because it's not good for you. You'll get a really bad headache. Alright? So, when you flip yourself over, the blood in your system is above your head, and so you have higher pressure in the lowest part of your body. Alright? Okay, we got to talk about a couple things quick. Let's continue our blood question. Alright, so here we go.
Start on that.
Here you are. You're laying. It's not dead yet. I'm not dead yet.
Is that a coffin?
All right. You're not feeling too good. You go to the doctor. They hook you up to a bag of IV of some kind. Okay, they take the IV, which is a bag of fluid. They have the tube, which has fluid in it. They punch it into your vein. Now you and the bag of fluid are one fluid system. And then they take that bag and they raise it up high.
And then they squeeze it.
And sometimes they will. Like for instance, if you're really bad dehydrated, they'll squeeze it to put more fluid into you faster.
But if you're already hydrated, it's not good.
Alright, now, everybody, blood pressure. You know what blood pressure is? What's standard blood pressure? 120 over 80? Okay, 120 over 80, that's 120 millimeters of mercury over 80 millimeters of mercury. What that means is this, okay? That means is this. The higher one is when your blood is pumped by your heart. That increases the pressure in your system. And so that's your high blood pressure spike, when your heart pumps the blood. The lower one, 80, is when your heart is at rest, in between pumps, in between beats, and that's the low pressure in your system. Okay? So you have a minimum pressure of 100 millimeters of mercury. What the heck's millimeters of mercury? Where do they get that?
We got that.
760.
Well, they get that from one of these tubes.
And they just put mercury in there.
If this is filled with mercury, mercury has a really ridiculous density. It's like 13,600. Okay? Please stop it. All right, 1360 kilogram per meter cube density of mercury. And so what they're doing is they're working backwards from this to find pressure. Okay? This rho GH equals a pressure, right? So that's where they get this millimeters of mercury thing. All right? Now, in your packet, I tell you the conversion between millimeters of mercury and regular pascals. It's on bottom of page 5.
760 millimeters of mercury.
So 1 millimeter of mercury equals,
Oh, no, that's
no. 1 millimeter of mercury equals 130 pascals. Okay, so what is your real pressure? Convert this into high and low pressure in pascals. So you multiply it by 130. So what do we get here? 15,600 over, what was it? 10,400. And that's in pascals. Okay, now wait a minute. Are you telling me that your blood pressure is less than atmospheric? Whoa, that means that...
we get crushed.
Okay, we need to talk about the difference between absolute pressure and gauge pressure. All right. Okay, everybody, right here? You see this right here? This is ABS, absolute pressure. Absolute, that's the real pressure in nature. Okay, you see this part right here? This is called gauge pressure. It's just the pressure due to the fluid, not because of any of the pressure on top. So in general, gauge pressure is absolute pressure minus the atmosphere. Okay, the reason they call it gauge pressure is because, like, for instance, has any of you ever measured the air pressure in your tires?
Yeah.
Okay, when you take that air pressure gauge and you hold it out in the atmosphere, what does it read?
Zero.
It reads 0. It only measures the pressure above atmosphere. Does that make sense? So that's what they call gauge pressure. It's the extra pressure not counting the atmosphere. Okay? So this is gauge pressure. Your pressure, the absolute pressure inside your body is actually this plus 100,000. Okay? This is gauge pressure. So that's just the MGH. All right, now, if you want this fluid, say you've been in an accident, you need blood. If you want this blood into your body, how high do you have to lift this thing before it goes in? Because if you cut yourself, your body pumps the blood out because you have a higher pressure inside than outside, right? So if you stick a tube into your vein and you want fluid to go in, you need to push it in. You're all grossed out now, aren't you? So what do? You take the bag and you raise it real high. How high?
I don't think nurses measure the height.
Rho
1.516 meters. 1.516.
You have to overcome at least this pressure.
Oh well, I'm talking. I did the math.
Yeah. Okay, here's the deal. If you overcome this pressure, it'll flow in continuously. If you overcome only this pressure, look. Yeah, exactly. It'll go squirt, squirt, squirt,
And
squirt in between heartbeats. It'll
And
squirt
it'll
in.
come back out too, some of it.
Well, they have a one-way valve.
So 1.01. No, it's come standard.
So this has to equal at minimum this.
Mr. Bruin.
And we put in, pascals, and we put in the density of blood and G, and we come up with the height. And what is it?
1.01.
1.01 meters. Okay? So it has to be at least 1 meter. If you want it to go above this, then it's about 1.5 meters. And think about that. How high are those stands that hold the IV bags? Taller than you, right? So if you stand up, they're still going to go into you. Okay? If you don't like taking your medicine, what do?
Knock it down.
You raise your arm up, and it won't go in.
Or you knock
Wait,
it
what?
down.
He's not dying because
No, you don't want to
Or,
knock it down.
let's say in the middle of the night, you have a bad dream, and you knock over the stand, and so now the bag,
It's
is
draining
now-
your blood.
It's
What
a
would
one-way
happen?
valve.
It drains your blood until it gets
It's a
full.
one-way valve.
oh, it drained your blood out. That's called giving blood. How many of you have given blood? What do they
had blood
do? They
tests
stick a
done.
tube in your body, and where do they put the bag?
Down there.
Down low. That's called IV in reverse.
I cannot.
Now, in the real world, what happens if your IV bag falls over? They've got a one-way valve in that thing, so it can only flow in but not out. But when you give blood, the one-way valve is the other way, so it only pours out of you into the bag. Now, everybody, here's your next lab. When you go home tonight and you're taking your bath after taking your swim in the Trinity. Okay? You're in your bathtub.
What are they doing?
I want you to take a clear glass, a tall clear glass, into the tub with you. Be careful, it's glass.
Then drop it.
Okay, then do this. Take your glass. Step 1,
Upside down?
submerge the glass. Step 2, flip the glass over. Step 3, pull the glass out.
Oh, I think that'd be
Yeah, it's hard.
Oh yeah, it's hard to do.
No, water keeps.
Do we let it fill up?
Okay, a
completely?
couple of things that you'll notice. Number 1 is you'll immediately notice that the cup seems really heavy. And the second thing you notice is that, hey, this cup is still filled with liquid, even though the bottom of the cup is now above the water of the level of water in the tub. And so you do it over and over.
Just about.
Yeah, because it's kind of
I put
mesmerizing.
paper in there, like, once it was like that, and it's the paper was still dry. Something like that.
Oh, really?
Yeah. I just something like that.
Isn't it like
Hey, take a goldfish bowl in with you, with your goldfish, flip it over, and then pull it out, and then the goldfish will swim up here. Now, if you completely fill the cup with water, and you flip it over, it'll be completely filled with water all the way to the very top.
Why?
Okay, the question is why? Okay, this was Torricelli's question.
Chelly?
Torricelli,
Chelly?
you know.
And so
Torricelli.
I'm just saying what he says. Well, Dr. Fauci.
Not tortellini, Torricelli. Okay, now, the question is number 1 is why, and number 2 is, how tall can I make this cup?
To where it won't drain a little
it
bit.
has to be a,
Will it go up infinitely far?
you have to have an infinitely deep back.
Nice. Alright, so what Torricelli did is he said, well, I'm going to do this with mercury, because the mercury is more dense. So he got into his tub of mercury.
Like, really?
Oh my god.
He got into his tub of mercury with his glass cup. Except he used like a long tube, okay? You want to see how far it would go. And what he did is he put the tube in here, and the tube was completely filled with mercury, and then he propped it up. And when you prop the thing up, it goes like this. He reached this magical spot
Where it would.
where it would only go so far. And if he had one that was shorter, it would fill all the way to the top. But if he had one that was taller, it would only go to this level. Okay? Does that make sense?
Yeah.
And so he's like, first of all, why? And second question is what the heck is up here?
Nothing, eh?
That's what he came up with. He came up with the first idea of nothingness, a vacuum. Because he said, look, there was mercury in it, mercury gone, nothing got in, must be vacuum. Okay, so he created and came up with the idea of a vacuum. This is our first vacuum. Okay? Because there's nothing in there. Whoa, what's the pressure of a vacuum? 0. Wow, the pressure on top is 0. Okay, work with me. The pressure on top is 0. What's the pressure right here?
More than 0.
The pressure right there is rho GH plus the pressure on top, but that's 0. So it's just rho GH, right? But that pressure right there is exactly the same pressure as right here. And what's the pressure there?
1 ATM.
Why 1 ATM?
Because the only thing pressing down is there.
Because you have 1 ATM pushing on it, and if it's not in equilibrium, then it would be moving, right? So the pressure in the fluid here must also be 1 ATM, right? So right here, this is 1 ATM. So what he said was, look, pressure at this spot equals P naught plus rho GH, but the pressure at the top is 0, and this is 1 atmosphere. And that equals rho, which is 13,600 for mercury. G is 9.8. And what's the magic height?
That.
Whatever we wanted.
So what are you trying to solve?
That.
I'm solving for the magic height.
got it, don't worry.
What did you already know?
0.75?
0.75 of a meter. So the deal is no matter how tall this cup was, as long as it was greater than 0.75 of a meter, the water, the mercury, would stop at 0.75 of a meter and never go any higher. Okay? And then what he found was that the next day the height was different.
Because different conditions?
Because what he built was the first barometer. Because now the atmospheric pressure here, which changes from high to low, changes the pressure here, which can be measured by the change in height here. So on a hot, sunny day, the liquid would move farther up in the high pressure. And on a cloudy, rainy day, the liquid would move down a bit to low pressure. If you convert this, everybody, into inches, don't start cleaning up. I got minutes left.
That's right.
If you convert this into inches, it's about 30 inches. Now, next time you hear the weather report and they talk about the barometric pressure, they'll talk about the barometric pressure in inches of mercury, which is this. Normal atmospheric pressure is about 29 to 30 inches of mercury.
Is it?
It's like it's almost 30. Okay, it's 29 point something. Okay?
Alright.
All right, now I'm not done yet. I'm not done yet. Of course not. Okay, so here we go. If we have your bathtub again, and you take an object into your bathtub, hey, I'm going to hold you through lunch if you don't quit packing up. I don't care. Stop it. All right. What's the pressure on top like?
Well, pressure of air plus the pressure of the water?
It's P naught plus rho G H. What's the pressure on the bottom line?
Same
P naught plus rho
It's just different
G.
H.
Ooh, H.
Is that a box?
That's a box.
Is it bigger? Why is it bigger? Oh, okay, because it's bigger depth.
It's a bigger depth, right? How about the pressure on the sides?
Peanut.
Now they're going to be the same, right?
Yeah.
So the pressure on the sides will be equal to each other and cancel out. But will the top and the bottom pressures cancel out?
No.
What's going to happen?
Same.
You're going to get more pressure on the bottom than the top. So what's that object going to want to do?
Same.
It's going to want to float. This is called buoyancy force.
Okay.
Ruben, peanut equals Rajesh. Roji, Roji.
Oh, wow.
Poor little Rajesh. Okay, now here's what we're going to do. Is we haven't quite finished buoyancy force. So I'm going to move this e-homework back until Tuesday.
Oh, cool.
You'll have 2 e-homeworks on Tuesday now. Now, listen. The deal is, though, is the e-homework that's due on Tuesday, we've covered half the material. So you can already start the one that's already due on Tuesday. Okay? So that way you don't have too much e-homework on Tuesday night.
You said so like 10 times.
Wait, we have a e-homework the night